We had a great day, even though we forgot.
In the last part of this lecture, I want to talk about the proof of the one missing piece from our argument for the fundamental theorem of Galois theory. And that's going to involve first talking a little bit about characters. So a character chi of a group G with values in a field L is a homomorphism from G to L star. So the non-zero elements of L, the multiplicative group of L. So what is this? It's chi is a function from G to L star that is a homomorphism. So chi of G1, G2 is chi of G1 times chi of G2, where this is multiplication in this group G, and here we're multiplying in the multiplicative group of L. And it's really important that you send every element of G to a non-zero element of L. Okay, we're going to be looking at sets of characters. So what does it mean for characters chi1 up through chi(n) to be linearly independent over L? It means that they are linearly independent as functions on G. That is, if you can take an L linear combination, a1 chi1 plus a2 chi2 plus an chi(n), and get the zero function on G, where a1 up through an are in L, then all of these ai's have to be zero. Okay, so what does this mean to be the zero function on L? It just sends everything in G to zero. So if you have these a1 up through a1 up through an in L, such that this combination is zero, that means a1 chi1 of G plus a2 chi2 of G plus an chi(n) of G is zero for all elements G in the group. Then it has to be the case that each one of these ai's is zero in L. Okay, so that's what it means to be a character. This is what it means for a set of characters to be linearly independent over L. Theorem 7 in section 14.2, which I'll prove in this video, is about linear independence of characters. So if you have chi1 up through chi(n) being distinct characters of G with values in L, meaning they don't send, there are no two characters that send every element of the group to the same place. So any two characters have to send at least one group element to different places. So if these are distinct characters of G with values in L, then they are linearly independent over L. Okay, so who cares? Like, why are we talking about this now? Is an example of characters comes from field embeddings. So if sigma from K to L is an embedding of K into L, so an injective homomorphism from K into L, then it gives a homomorphism of the multiplicative group of K to the multiplicative group of L. Sigma from K star into L star is a homomorphism. So what is that? It is a character of the group G equals K star with values in L. Okay, so just to check, we have this homomorphism from K star into L star. What is going on? Like, how do we know that that actually is what happens? Well, we know that sigma sends 0 to 0, an injective homomorphism of fields, but sigma doesn't send anything else to 0 because part of the definition of an embedding is that this is an injective homomorphism. So if you have a non-zero element of K, it gets sent to a non-zero element of L. So sigma of 0 equals 0, but sigma of alpha is not equal to 0 for any alpha in K star. So you really do get a character of G with values in L, a character of K star with values in L from this field embedding. Okay, so field embeddings give characters. Then what does linear independence of characters say about embeddings? So if you have sigma 1 up through sigma n being distinct embeddings of K into L, then they are linearly independent functions on K. Okay. We've talked a lot now in the proof of the Galois correspondence about sets of embeddings. And one thing that we noted that was important is that automorphisms of K are embeddings of K into K. So in particular, we can apply this statement to automorphisms and see that distinct automorphisms of K are linearly independent as functions on K. And this is the statement that we're going to use in the proof of this theorem 9, this difficult piece of the argument for the fundamental theorem of Galois theory that I skipped over at first. Okay, so I'll pause and erase. First, I just want to point out that corollary 8 follows very directly from theorem 7 applied to this setting where your characters come from field embeddings. So all we have to do now is prove theorem 7 on linear independence of characters. So I'll do that next. Let's prove theorem 7 on the linear independence of characters. So if chi1 up through chi(n) are distinct characters of G with values in L, then they are linearly independent over L. And the proof idea is simple to remember. So we're going to argue by contradiction. We're going to suppose that chi1 up through chi(n) is a dependent set of characters over L. And the big thing to remember is there may exist many relations. A1 chi1 plus 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 an chi(n) is 0. What is the thing that we're going to contradict? We're going to choose a relation with the minimum number of non-zero coefficients. So if you remember this part, the rest of the argument should go forward in a pretty straightforward way. Okay, so we're going to do that. There may be many relations. We're going to choose one with the minimum number of non-zero coefficients. And we're going to use something to find a non-zero relation with a smaller number of non-zero coefficients, and that will be our contradiction. Okay, so let's choose our relation with the minimum number of non-zero coefficients. We can rename which character is chi1, which one's called chi2, which one's called chi(n). So reordering if necessary, this gives a relation a1 chi1 plus a2 chi2 plus 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 am chi(m) is 0. So it's the 0 function on G, where each one of these ai's is not 0. So here we have m non-zero coefficients. And what we're going to do is find a relation that is not all of the coefficients being 0, but it has fewer than m minus 1 or fewer non-zero coefficients. All right, so if this is our relation, then if we take this 0 function and apply it to G, then for any G in our group, we have a1 chi1g plus a2 chi2g plus 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 am chi(m)g is always 0 for any G. Okay, so how are we going to get a relation with fewer non-zero coefficients? We know that our characters are distinct. So in particular, let's say chi1 and chi(m) are distinct. So there's some element in the group that they send to different places. So chi1g0 is not equal to chi(m)g0. Okay, each chi(i) is a homomorphism. So what we can do is instead of taking this function and applying it to G, we can apply it to G0 times G. And what does that give us? Well, G0 times G is still in the group, so we're still going to get 0. So a1 chi1 G0G plus a2 chi2 G0G plus 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 am chi(m) G0G is 0 for any G in the group. But each one of these chi's is a homomorphism, so we can take the chi(i) G0G part and write it as chi(i) of G0 times chi(i) of G. And remember, chi sends elements of the group G to non-zero elements of this field L. So what do we get? We get a1 chi1 G0 times chi1G plus a2 chi2 G0 times chi2 of G plus 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 am chi(m) of G0 times chi(m) of G. And this is always 0. So now we have this equation and we have this equation, star and star star. And we're going to multiply star by chi(m) of G0, and we're going to subtract star star. So this is the other big thing to remember here is how are you going to find a non-zero relation with a smaller number of non-zero coefficients? We're going to play these two equations off of each other. So multiply star by chi(m) of G0 and subtract star star. And what we get is chi(m) of G0 minus chi1 of G0 times a1. these are two elements of this field L, times chi1 of g, plus chi m of g0 minus chi m minus 1 of g0, times am minus 1, times chi m minus 1 of g. And then the last terms cancel out, right? The last term here and the last term here, when you multiply star by chi m of g0, what we get is chi m of g0 minus chi m of g0. This is obviously 0 times am times chi m of g equals 0. So now the chi m of g coefficient here is 0. The chi1 of g coefficient is not 0 because we know chi m of g0 minus chi1 of g0 is not 0, and we know that a1 is not 0. So what have we gotten? We've used this relation with exactly m non-zero coefficients to find a non-zero relation where now this coefficient is 0. We don't know how many coefficients are non-zero, but it's at least 1 and it's at most m minus 1. This is a non-zero relation with fewer non-zero coefficients. So this contradicts our choice of taking a relation with the minimum number of non-zero coefficients. Okay, so this idea is clever. If you remember this part, then you can probably remember how the rest of it goes. This idea is something that's going to come back when we talk in the next video about the proof of Theorem 9, which uses a similar proof by contradiction strategy, but it's more complicated.